Okay, so this is lesson 7 in the polynomials unit on factoring special polynomials. The polynomials we're going to be factoring today involve perfect squares. So I just want to review what perfect square numbers are before we get into perfect square trinomials. Perfect square numbers, let's just write this at the top of our notes here. Perfect square numbers are numbers that can be written as a product of two identical factors. We call them perfect squares because you can take that number of objects and make it into a square shape. So 25 is a perfect square, for example, because 25 can be written as 5 times 5. Or 16 is another perfect square because it can be written as 4 times 4. So whenever you can write a number as a product of two identical factors, it's called a perfect square. So polynomials, trinomials in particular, can be perfect squares as well. So first we're going to look at some trinomials and how to identify if they're perfect squares or not and how their factors look when we factor them. Once you've identified that a trinomial is a perfect square, the factoring process is actually easier than a process like something like decomposition. Okay, so let's look at the first example here. This is a trinomial where the leading coefficient is 1. So let's try and factor in the normal way. So we'll solve our little number puzzle here where we try to find two numbers where the product is 9 and the sum matches the coefficient 6. We should be used to doing this type of factoring since lesson 4. Okay, so if I try and think of those two numbers, they would be 3 and 3. Right? 3 times 3 is 9, 3 plus 3 is 6. Whenever you notice that you solve the little number puzzle and the factors or the numbers that solve it are identical, you actually know that this is a perfect square. That means the factors are going to be identical as well. Okay, so in this case, my factors are going to be, so to make the x squared term at the front, I need x times x. And then to make the 9 at the back, I'm going to need 3 and 3. And everything is positive here. So it's going to be positive 3 and positive 3. That's my factored form. And notice that the factors are identical. They're the same. That's why it's called a perfect square trinomial. You could also write this in a more efficient way as x plus 3 all to the power of 2, since the factors are the same. Either or, both are correct. Okay, let's do one where the leading coefficient is not 1. Remember, the puzzle is pretty similar. Instead of finding a product that makes 9, though, this time we're finding a product that makes 3 times 4, right? We multiply those together. So we're looking for a product of two numbers to be 36 and their sum to be 12. Okay, so if we think of the two numbers, yeah, they're 6 and 6. Okay, identical. So that means we have a perfect square. So whenever you're solving and you find that the two numbers that solve the number puzzle are the same, we know the factors are going to be the same as well, and we've got a perfect square trinomial. Now this time the way we factor, we don't have to go through the whole decomposition process if that's what we're doing. We just have to look at the first and the last term. And we know the factors are going to be identical, so that's our clue to solving this. Okay, so let's look at the first term here. I'm going to use a different color. The first term, when I multiply the first two terms of our factors, they're going to make 4x squared. And I know their terms are going to be the same. So the only way to do this would be to multiply 2x and 2x. Those must be the first two terms of my factors because when I multiply them out, it makes 4x squared. Okay, let's look at our last term. I'm going to use a different color here, 9. So when I multiply the last two terms of my factors, I'm going to get 9. So that means they must be 3 and 3. And everything is positive here. So it's going to be positive 3 and positive 3. There are my factors, 2x plus 3 and 2x plus 3. Or we can write this as 2x plus 3 squared. So again, one of the easiest ways to identify something as a perfect square is to solve the number puzzle like you would when you're doing decomposition. And when you see that the two numbers that solve the puzzle are the same, we know we must have a perfect square. The factors are also going to be the same. Okay, this would be a good time to pause the video here and see if you can solve the last one. And then come back and check with me afterwards. Okay, hopefully you're back from solving. Here we want to solve the number puzzle where we have a product of 100 and a sum of negative 20. Okay, so this time our middle term is negative. So our factors will have some negatives in them. Okay, and the two numbers that solve this are negative 10 and negative 10. So they are the same. That means I have a perfect square trinomial. And I can go straight into factoring it because I know the factors are identical. And we want to use the first term and the last term as clues for what my factors should be. So let's look at the first term together. It is 4y squared. That means the only way to get this using two identical terms would be 2y multiplied with 2y. That would make 4y squared. Okay, perfect. Now I'm going to look at the last term, 25x squared. Okay, so I'm going to have two identical things that would multiply to make that would be 5x and 5x. Now I know the middle term is going to be negative, so I need a negative sign in between these two terms so that when this FOILs out, I get that negative term in the center. Okay, we could also write this a more efficient way. Again, it's up to you how you want to write your final answer, but it could be written as 2y minus 5x all squared. So these are called perfect square trinomials because the factors are the same. So just take a second here to pause the video and in your own words, describe how you can tell if a polynomial is a perfect square trinomial, and then give another example where you would have that. Okay, we can tell when the factors are the same. When you're solving the number puzzle and you get two identical numbers, you know you're going to have a perfect square trinomial. So when you're factoring when factoring by decomposition, the two numbers are the same. Actually, I'll put the two numbers in step 1. The two numbers that solve the puzzle. There are other ways to tell, but I think that's easiest given how we've been factoring all along in this unit. You can give any example you want. I'm going to give one here. X squared plus 16x plus 64. That would factor to x plus 8. X plus 8. Okay. Let's look at another one. This one is similar, but instead, there's actually the middle term is missing. So we call these a difference of squares. Just have a look, take 10 seconds to kind of look at these and see why you might think we call them a difference of squares. Okay, so the reason they're called a difference of squares is because we'll see here in all of them, there's a difference, right? A subtraction sign, that's called a difference. And then on either side of the subtraction sign, there's a perfect square. Except for part C, there's going to be something special with that one. Yeah, so essentially the middle term, they would be trinomials and we can factor them the same way, except the middle term is missing. In fact, you can think of this first one like x squared plus 0x minus 36. Okay, so if we notice that there's a difference of squares, the middle term is actually 0. We can start solving the number puzzle, and after a while you actually don't even have to solve the puzzle anymore because you'll just recognize these and know how to solve them, but we'll do it the first time. So the number puzzle says we're looking for two numbers that multiply to make negative 36, but this time add so that there's no middle term at all, so that the middle term is 0. So the two numbers that solve this are negative 6 and positive 6. there I've got my two factors. Since this leading coefficient is 1, I'm just going to write them down, x minus 6, x plus 6. So it's almost like a perfect square trinomial. They're almost the same factors, except the middle term, or in the middle, the sign is different. So whenever you notice there's a difference of two perfect squares, you can factor this way. They're going to be, I'll just summarize that here. The factors are identical, except the sign differs. Right? Okay, let's have a look at this one. Here we notice, okay, 49 and 25, a squared, b squared, those are perfect squares. So this is a difference of squares. Once you notice something is a difference of squares, you can just go straight into factoring. Let me show you how. We know the factors are going to be identical, except for one factor is going to have a plus sign and one of them is going to have a minus sign. That's because that middle term gets canceled out to make 0. Okay, so let's look at the first term here. When I factor this, or when I FOIL this, the factored form out, oops, sorry, just going to do this so it doesn't get too cluttered up. Those two middle factors, or the first two factors, the first two terms, sorry, will get multiplied out and make 49a squared. So the only way to write this would be 7a times 7a. 7a times 7a is 49a squared. Perfect. Okay, so let's look at the last term, 25b squared, and make the other two terms in our factor. When those get multiplied out, I get 25b squared. So the only way to do that while keeping the terms the same would be to use 5b and 5b. So the factors are the same, except for the signs in the middle are different. Let's actually FOIL this out and see what happens, just because it's our first time doing it. So we get 7a times 7a, which is 49a squared. Then 7a times negative 5b, that's negative 35ab. Now we've got another positive 35ab, and then minus 25b squared. See how those middle two terms are the same but opposite signs? So when you add those like terms together, they make 0. So we end up with 49a squared minus 25, oops, b squared. So this is a difference of squares. The factors will be the same except with opposite signs in between the terms of each factor. Okay, let's look at the next one. This is a good reminder here of the first step we should always think about when we're doing factoring questions, which is pulling out a common term or factoring out a common term before we start, if there is a common term. This one has a common term of 5, so let's pull that out. Before we even start thinking about what type of factoring problem this is, we should always be, oops, taking out a common term. There we go, sorry. So 5 and then x squared minus 16y squared. Okay, the 5 is going to be part of our answer. It's a factor of the polynomial. But now what's remaining, we can factor it further. And we notice again that this is a difference of squares. The coefficients are both perfect squares, right? We have 1 and 16. So let's go straight into factoring. We don't have to do any decomposition or any longer method. Let's look at that first term, x. That's what we'll get when we multiply the first two terms of our factors, so x and x. And then let's look at the 16y squared. That's what we'll get when we multiply the last two terms. So 4y and 4y, and we know for difference of squares, the middle term is gone. So we need to put a plus and a minus so that the middle term cancels away when you FOIL everything out. So that's our fully factored form here. So that's a difference of squares with an extra common factor of 5 that was factored out at the beginning. Okay, so just pause the video here. I recommend to pause and just, in your own words, describe how you can tell if a polynomial is a difference of squares. So, in my words, a difference of squares would be a polynomial that is a difference in brackets, you can put a minus sign, that means subtraction, of two terms that are both perfect squares. When you notice this, you don't have to do any decomposition or any lengthy method. You can just go straight to factoring. So let's say I'm going to pick two random perfect squares. Let's say I have 64 x squared minus 9 y squared. 64 and 9 are both perfect square numbers. So this is a difference of squares. And the way I would factor it would be to look at the first term, 64x squared. To get 64x squared, I would do 8x times 8x. And then I would look at the second term, 9y squared, and split that up into two equal factors, 3y and 3y, and then a plus and a minus. I encourage you to come up with your own example and factor it as well.